Okay, so there are a couple of questions basically here where they were actually quite difficult, and I've not included the material on the exam. So I've decided, and I also looked, and the few people who have attempted them only didn't get the full credit. So what I thought I would do is I just kind of remove them from the homework, and just kind of you started it and you were just interested, I've just given you a quick video to show you how they work, and you will get credit for the question regardless on the homework. Okay, so this first one here, this is a chi-square goodness of fit, but it's like a very complicated chi-square goodness of fit. Basically, what we're doing is we have some data, and we want to compare it to data from the normal distribution. So the null hypothesis here is that the data are sampled from the normal distribution. And what we're going to try and do is prove that our distribution is different from what would happen if we had the normal distribution. And again, we haven't done a lot of probability in this course. It's using probability functions. So this was actually quite a difficult question. And the alternative hypothesis is like the opposite. So data are not sampled from the normal distribution. Okay, so let's just check our answer. And hey, we've done the first part of it. Okay, so what we need to do now is basically we've got a load of data and of expenses data, which we're checking is normally distributed. And we want to kind of put it in these bins and then compare the frequency in these bins of what would be expected of normal distribution. So let's just grab our data, open in an Excel. Okay, and I'm just going to kind of copy it over. I created a little template for this question before I decided to remove it. And the first thing I did is I had the bins that were basically, I didn't make these up. These were the bins from this particular question. So I basically put these into the spreadsheet. So let's just kind of put these in my raw data. Now we have the bins. These are just the upper limits. So this is exactly what we did when we did the histograms a couple of weeks ago. So sorry, I think it was the chapter 4 material. So all we have to do now is we have our data in column B, and we have our histogram. Our bin limits in column C. So let's go to data, and let's go to data analysis and histogram. And you can see this is because I was playing around, I was doing it before. We have basically the input range is B, 1 to 53, and the bin range is C1 to C10. And we're going to output in the next column D1. Okay, and we'll just remove them all. Okay, and the next thing we want to do is let me just check I've got this right. So we have the mean standard deviation and the N on basically C12 to C14. And for this, we need this because we're kind of going to see what we'd expect if we had a normal distribution with this mean and standard deviation, what we'd actually kind of, the frequency that we'd expect. So the X bar is just going to be average. And here it's going to be, we had B1 before because we included the labels, but it's just going to be B2 to B53. So that's our average. And let's just kind of copy our cells. And we're going to have the standard deviation for our sample. So stdev. That's our standard deviation. And finally, we want how many items we have, because we need this when we do calculate the chi-squared. And this is going to be like this. Okay, so we have B2 to B53, we have 53 items. Now, the next thing we want to do is we want to find out, if it was normal, a normal distribution, what would be kind of the cumulative distribution function? So we've got normal and cumulative. So this is what we're going to be kind of eventually, when we kind of turn it into a frequency, what we're going to kind of calculate it as. So we have here the, we're going to use the normal function, and we're going to do norm dot, and we're going to do, because we have the actual values and we want the probabilities, we're going to use the norm.dist. And we want to see, how much by up to 100 would we have if it was normal, given that we have a mean of this and a standard deviation of this, and cumulative equals true. So basically, now we don't want the mean and the standard deviation to change. So let's just lock them in when we drop down. And these are the normal, the kind of the cumulative normal probabilities based on the normal distribution. Okay. So I think, what exactly do we have to fill in here for this question? So let's we got a little bit ahead of the question. So let's fill in the frequencies. Okay, excellent. And yeah, this is not the one with help me solve it. I'll give you an example. So this is basically, we now have to calculate the chi-squared. Go away and calculate it. So this is kind of the normal kind of cumulative. And what we want to do here is kind of work out what we would do if we had like non-cumulative. So how much of the proportion is in each of these bins if it was normal. So the first one, this is just going to be F2. So this is just like the normal non-cumulative, so normal probability. So the first one is just F2, but the second one is the probability minus the previous probability because it's cumulative. So it's going to be this one minus this one. And then we're going to drag it all the way down, Control D, and we have these kind of different probabilities here. So this is kind of what we have, and this is what we'd expect if it was normal, but at the moment it's a proportion. So we'd have like the normal, the expected frequency if it was normal, and this would just be the normal probability multiplied by the n. So this is going to be times the n. And again, we don't want the n to drop down, so we're going to put $1 on it. And then we're going to drag it down. So we've got our actual frequency and the frequency if it would be normal. And let's just, this is where I kind of summarize my data. So we're going from 16 down to here. And this is where we put the chi-squared. So the chi-squared is basically, I'm just going to do a one for each, the kind of the partial chi-squared for each row. And okay, so that's going to be based on the formula. And this is the formula. It's like the last page of chapter 7. And it's going to be 272. Sorry. Did we have the? I don't think it even gave the formula. That's one of the reasons not for not having it. But it's basically, it's like the other chi-squared test. It's observed minus expected squared divided by expected. So it's going to be observed minus expected to the power of 2 all divided by expected. Okay, and now we're just going to drop this down. And basically, this is with chi-squared, you always add everything up. So we're just going to sum these values. And we get a chi-squared of 5.42. So now, let me just type this in. And there'll be some quick video editing if I've messed up. So type into 2 decimal places. So yeah, 5.42. Whoa, no video editing is required. Now, let's just kind of say if our alpha was 0.05. Oh, no, we don't need to put it there. I had already done it there. So we had 0.05. Our critical. Now, this is where this one's a little bit tricky, which is one of the reasons why I didn't want to include it in the exam, because I've taught this type of chi-squared before, and all my examples have been much simpler. So we always use the right tailed function with the chi-squared. I like in the example video I gave you for the chi-squared association where I drew the chi-squared. And the probability is going to be my alpha, and it's from the right tails. Now, interestingly, the degrees of freedom, most kind of multinomials, it's basic, most of this kind of chi-squared goodness of fit. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. We have nine kind of bins, 9 categories. So we'd have 8 degrees of freedom. But here, because we're modeling a normal distribution, we lose 2 degrees of freedom. Another reason kind of why I didn't want to put this on the exam, because I think the book almost kind of complicates this topic a little bit. It's actually quite a nice little simple test, but we seem to have very complicated scenarios here. So we have the let's just get this right. We have the probability of our alpha there, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9, minus 6 degrees of freedom. Our p-value is the chi-squared dot dist.rt. Remember, you use dist if you're converting a value to probability, and you use an inverse if you're converting a probability to a value. So, and with 6 degrees of freedom. And so my p-value is 0.49, and it'll be 1 if we've got 3 decimal places. And does it say 3 decimal places? 0.491. And again, hopefully no video editing. Yes, we're on a roll. So the p-value is larger than 0.05. Therefore, we fail to reject the null hypothesis and conclude that the normal distribution is a reasonable model for the data. Yep. Okay, so there we go. And as I said, I'm just going to, this question is a little bit overcomplicated. I'm just going to, I can remove after I've set the homeworks, and basically you just get the point for this. But if you kind of had made a first attempt at it and you were wondering where you went wrong, then just kind of, well, you've obviously watched this video. Thank you.